Guarda, guarda, come diceva questa prima, I don't have to.
Classic university technology, you just have to touch it and jiggle it.
Yeah, I don't. No. I'm looking for First one.
Oh, it's 6:70.
Yeah, absolutely. I'm thinking I can actually want to take one. Where even. But it's gonna time. You already finished last year. So it's over 8 hours.
It needs to look I got person soon. Okay, it's 5:30. Let's go and get started. All right, good evening, everyone. How's everyone doing today? Good, good. All right, so today we have another lecture on meshing. So again, this week, a little bit of a mismatch of different topics. So we're going to be jumping around a little bit, but these are all kind of important information with regards to. This will be kind of the last of this kind of lecture series on meshing. I know we've been talking about it for over a month now. But meshing is really important. So, but after this, we're going to get into more of the advanced features within ANSYS, but we have to talk about meshing one more time. Okay. I don't think there's really any announcements. Oh, I did grade your guys' activity 3s yesterday, so I apologize for that delay. I did try to leave comments on your activity. So please take a look at those comments. I try to write those comments with stuff that I think would be helpful as you guys kind of prepare for the midterm project. So in terms of, how to write the reports, how to frame how to frame the screenshots, just some feedback on your meshing, just based on kind of what we've been talking about. So definitely check that out, especially as you kind of get rolling on the midterm. Any questions I can answer before we get started for today? Okay, all right, so let's go ahead and keep going. Okay, so last time, we spent quite a lot of time talking about meshing. More specifically, how to refine your mesh in terms of your simulation results, right? And so we talked about the importance of looking at your results, seeing where your solution magnitudes are really high, stress magnitudes are really high, and how to refine your mesh in terms of that. Okay. Today I wanted to start with a kind of a different topic, which is to kind of explain to you how the hex dominant method in ANSYS works. Okay, so the hex dominant method is an option that should be familiar to everyone in the class. This is the primary way in which ANSYS will produce a hexahedral mesh. And let me start by saying that this is actually quite advanced. And so having a hexahedral mesher and having it be kind of a default option within the finite element software, this is not something that's common. Because producing a hexahedral mesh is normally very, very difficult. So the fact that this is an option in ANSYS is actually a very, very nice feature. And it's actually one of the main features why, or one of the main reasons why ANSYS kind of sees a lot of widespread use. So actually, before I came to work here about 6 years ago, I primarily worked with more research softwares for my finite elements. And basically all the research softwares out there, they only have a tetrahedral mesher. And so, we learned, when I was in grad school, I learned about a hexahedral mesh, but it was kind of more like a myth, oh, this would be really nice if we could do this. But ANSYS just gives it to you. ANSYS just said, like, here, you can make a hexahedral mesh, and we'll make it really easy for you to do so. It's like, wow, this is really, really cool. Okay, so how it works is actually very interesting. The exact details of how it works, I think, is proprietary within ANSYS, and so we may not know exactly how they choose to do certain things. But the rough idea, ANSYS has been comfortable with kind of sharing that detail with us. So when you select a hex dominant mesh, what actually happens underneath the hood is that ANSYS will actually first create a tetrahedral mesh. Then after producing the tetrahedral mesh, ANSYS will then try to smartly combine certain tetrahedrons together to form a hexahedron. And in quotations here, I'm gonna say smartly, because you know, how ANSYS actually chooses the tetrahedron to combine together. That's kind of the part that's proprietary. That's kind of what they don't really tell you. Because if you combine just two random tetrahedrons together, you're probably going to end up with a very skewed, very weird looking hexahedron. But you know, maybe there's something in the way that ANSYS creates the tetrahedron mesh. Maybe there's something in the way that how they choose to combine them together. You know, oftentimes when it works, it produces a very nice, you know, well-behaved mesh with very nice kind of looking elements. All right, so it's a little bit hard to show this in 3 dimensions, just because I'm kind of drawing a 2-dimensional surface here. So I think I'll show you what it looks like in 2 dimensions. Okay, so let's say we have a triangular mesh like this. And so basically, if you're working in 2 dimensions, the quad dominant mesh kind of works exactly the same way. And so if we have a triangular mesh that looks like this. Okay. Right here is a 2D triangular mesh. Okay. So what ANSYS will do is that it'll look at pairs of elements together and say like, all right, which pairs of these will, you know, make a good quadrilateral, will make a good hexahedron, okay? And so it'll identify, you know, elements that, you know, maybe like these two right here, okay? So if we combine these two together and we kind of eliminate that kind of dividing line in between them, that's going to give us a pretty good looking quadrilateral pair, okay? Same thing for these two elements here. And we'll say these two elements here, okay? And so if you combine all these together, you end up with a mesh that looks like this. You can see that that mesh of 7 triangles became a mesh of 3 quadrilaterals here and 1 triangle. Okay. Notice how, you know, sometimes there will be cases where you know, a triangle or a tetrahedron may not have a partner, and so those mesh elements will still be tetrahedron or triangular. Okay. Hence the name hex dominant, and so it's very hard to produce a mesh that's entirely hexahedrons. It is possible, but you know, it is more difficult. But oftentimes you'll have cases like this, but for the most part, you know, it tries to combine them smartly together, and you know, in the mesh that results often looks pretty good, as if it were kind of naturally made with hexahedrons. Okay. Part of the difficulty of making a generic hexahedron mesh, at least kind of when I was in grad school, is that, you know, you can take any geometry and you can put a bunch of points or nodes in there, and have them, you know, be separated by a certain distance. It's connecting those nodes in a way that creates a cohesive mesh that's a bit different. So with tetrahedrons, it's a little bit more structured. It's a little bit easier, just because there's less connections to make per node. But for a hexahedron, you know, a node can belong to, you know, lots of different types of elements, and you know, there's a lot of different connections to make. And so this is kind of a very kind of clever way to do it. So to kind of start with a tetrahedron mesh, something where the theory is very well matured, it's very well developed in terms of creating generic tetrahedron meshes, and then combining elements together in a smart way to create hexahedrons, which, as we know, kind of has very nice properties for your solution. Okay, so that's kind of what's going on under the hood, and a lot of times, when you get errors, when creating a hex dominant mesh. It's either because, maybe the algorithm that they're using, they weren't able to combine, two elements together, or maybe one element had tried to find, multiple different partners, and that kind of created an error in a weird area. Or maybe the combination of certain elements, created a very kind of weird overlapping element. So, this algorithm is not perfect, hence why you get errors when you try to create a hex dominant mesh, but for what it does and for how versatile it is relative to kind of all the methods before it, it is actually quite clever and quite nice. Okay, any questions on the hex dominant method? Okay, cool. All right. So there are other ways to produce a hexahedral mesh. These next methods are a little bit more traditional. So these are kind of how they used to be done. So another method for creating a hex dominant method is to use something called a sweep. So this is a bit more traditional, but it's also not very practically useful. It's kind of more of a kind of a research thing, or kind of a proof of concept. I think that's a better way to call it. So the way the sweep method works is that, if you have a surface where you can produce a quadrilateral mesh, what you can then do is you can then sweep that forward through a volume and create a hexahedral mesh with that same stencil. Okay, so of course, this only works on very specific geometries. And honestly, for these geometries, the hex dominant method will probably perform just as well. So there's, for most cases, I would say there's not really any reason to use a sweep method, unless for some reason the hex dominant method was not working. But you're gonna see that this method here kind of takes a bit more setup to do. Okay. Okay, so let's say that we have a geometry that looks like this. So let's say we have kind of a square cross section. We have kind of a path behind it that kind of looks like this. Okay, so we have kind of a square channel looking geometry. Okay. So the idea with the sweep method is to look at a particular surface and mesh that surface using quadrilaterals, because generally it's a little bit easier to produce a quadrilateral mesh in 2 dimensions than a fully 3-dimensional hexahedral mesh. So step 1 in the sweep method is to mesh this with quadrilaterals. That's pretty easy to do in this case, and so we're just going to create kind of a cross hatch pattern here. Then what you can do is you can take this stencil, and so this stencil is going to form kind of the basis for your hexahedral mesh. Okay, and so if this channel right here, if it has kind of a constant cross section, then we can take the stencil and just sweep it through. So you can basically take this and sweep the stencil through the entire volume of the geometry. And so it tries to kind of maintain that same cross section. And that's the idea, is kind of to develop a cross section for hexahedron that kind of, is ideal. And then you try to maintain that cross section throughout, creating hexahedral elements along the way. Okay, so the way this works in ANSYS is that you have to define what's going to be your starting face, and you have to define where the target faces are going to be. So basically, the sweep is going to go from the target face to, or from the source face to the target face. Source face. So you're basically defining kind of the starting point and ending point for the sweep. So I think this was one of the first methods that was developed to kind of reliably create a hexahedral mesh that wasn't manual. Of course, for kind of for the early days, people created hexahedral mesh manually. So they kind of manually defined where all the elements are, where all the connections are. This is one of the first kind of automated methods or algorithmic methods to create a hexahedral mesh. But as you can imagine, this has very limited practicality, because this only really works for a very simple surface. And if you try to give it any kind of complexity, even just a changing cross-sectional area, it might fail and give you an error. Okay? But it's important to kind of see kind of how far we've come since then. Okay? There's a variation of this that you can do in ANSYS as well called a multi-zone method. So basically for the multi-zone method, you're going to be doing sweeps, but you're going to be doing multiple at the same time. So the idea with multi-zone is that this would be able to tackle more complex geometries. But again, because of the limitations of, supplying a source face and an ending face, even if you do it multiple times, there's limitations on this. So this option is available in ANSYS as well. And so if you had a geometry that, maybe this Texas looking shape here. Right, so you can define, maybe this region here we can do a sweep, this region here we can do a sweep, and this region here we can do a sweep. So multi-zone methods basically allow you to define different regions and perform a sweep in those ones. But again, this also has kind of very limited kind of practical applications. If you try to apply any of these methods to the midterm projects, I don't think you'll be very successful, just because the midterm project geometries are more complex than this. Okay. All right, any questions on these methods here? All right, so out of all the methods that we just covered, hex dominant is probably the one you're going to use the most, just because that's kind of an ANSYS special. It is the most flexible, but just know that there are other options available. And if you do have a geometry where you can do a sweep or you can do a multi-zone, you're probably going to get a little bit of a higher quality mesh using that, just because it's the algorithm for developing it is different. But usually it's kind of negligible, because hex dominant has come kind of a long way since it was first introduced. It's good to know that there are other tools available. Okay. And so, on that topic of hexahedral elements, let's dive a bit deeper into the convergence behavior of the different element types. Okay, so we've kind of talked informally about the difference in convergence between tetrahedrons and hexahedrons and linear elements and quadratic elements. But I think it's good to kind of quantify it all in using one kind of very common test case, right? So in this section here, we're going to compare mesh convergence using a simple example and different element types. This might be a good exercise for you guys to kind of do on your own too, just so that you can kind of see and you can kind of illustrate for yourself kind of how these convergence behaviors change. Because it's one thing to kind of talk about them, but to kind of see it kind of converge in real time it's good. Okay, so let's look at the simulation that we're going to do. And this data was all actually compiled, by not by myself, but by the author of the textbook that we're using. Okay. So he basically took a very simple cantilever beam. So a cantilever beam is one where we have kind of a fixed support on one side, beam that comes out. It's a three-dimensional beam, so we're not doing a 2D simulation here. Bless you. And we have a load that's being applied right at the end, and it's a bending type load. So okay, so very simple geometry, very kind of reminiscent to our ANSYS activity too, except with kind of a simpler geometry here. Okay, and so what they did for this test here that they ran multiple mesh convergence tests, and they compared the results between different element types. Okay. And the output of interest, or the output that we're looking at in the mesh convergence test, is simply just going to be the deformation at the tip of the beam. Okay, so let's do some comparisons. So we're going to do a bunch of kind of head-to-head comparisons here. So first, let's look at the comparison of a linear tetrahedron and a linear hexahedron. So two linear elements, but one is the triangular element, the other is the rectangular element. Okay, so we know just based on the shape functions and based on everything that we've been discussing that the hexahedron is the superior element, and so we should get better convergence criteria or convergence behavior with the hexahedron. But let's see what it actually looks like. Okay, so let me go ahead and draw the axes for our mesh convergence testing here. Okay, so on the horizontal axis, we have the number of elements. Or you can do number of nodes, or the number of or the cost of the simulation. That's essentially what this is. Okay. And on the vertical axis, we're going to be measuring the tip deformation. Let's plot out the convergence graph for the linear tetrahedron first. Okay. Okay, so the linear tetrahedron, let me use green for that. The linear tetrahedron, the convergence graph looks kind of like the following. So a pretty standard looking convergence graph here. And so it starts off low, and then as we refine the mesh, it gets higher. Okay. Now for these convergence graphs, I believe the way that they did this, they just adjusted the overall global size of the elements. So there was no local refinement, kind of like what we talked about on Tuesday. Okay. So this is just the overall number of elements. They just changed the overall mesh size. Okay. So now the important parts of this graph, not only do I want you guys to look at the shape, but I want you guys to look at where they start too. Okay. So the true deflection for the tip, you kind of write that first. Right. So based on the load that was applied here, the true deformation is about 0.75 millimeters. And we know that in this case, because the geometry is fairly simple, and there's actually an analytical solution, but you can also easily kind of verify this as well. And typically, if you refine your mesh enough, you should get there. So the true solution is 0.75. So we're going to see how quickly these different mesh elements approach 0.75, if they approach it at all. Okay. Okay, so let's look at the linear tetrahedron first. So this graph, where they started, they actually got a very large error. So at the left end here, the deformation that they obtained with the linear tetrahedra was only 0.3 millimeters. So it's less than half of what it's supposed to be. So with these, we have a very, very large error. And that makes sense because we know that linear tetrahedra, that's kind of the simplest element that you can use There's probably some shear mocking that's going on here, and so it makes sense that we have a large error. Okay. Now let's look at the linear hexahedron. And so this is a little bit hard to appreciate because the linear tetrahedron performs so poorly. But the linear hexahedra, the graph kind of looks like this. And so it looks like a straight line. And its convergence is right at 0.75 millimeters. Okay, so if you look at this graph right here, it looks like the linear hexahedra kind of converge right away. That's not true. So there is a little bit of convergence behavior that's going on. It's just that the linear tetrahedra kind of started out from such a poor spot. When you kind of graph these together, it looks like the hexahedra is just so much better. So this path here is this graph here is a little bit misleading because there is some error here. It just didn't find the right solution right away. There is some error there, but it's just so small compared to how big the error was for linear tets that it's almost unnoticeable when you kind of graph them together. And so this kind of illustrates kind of the a point that we've been talking about for weeks now. So just don't use linear tetrahedra for structural FTA. You can refine it. You can refine it enough in order to get a converged solution, but a lot of times it's just not worth kind of the headache to do so. And what's further interesting is that I kind of drew these graphs on purpose. Even if you look at the region here where both graphs have looked like they converge, there's still a little bit of error between the graph of the linear tets and the linear hexes. Okay, so even at fine mesh resolution. Even at fine mesh resolution, there's still a little bit of error between these graphs. Now, that's not to say that you can. I mean, you can of course keep refining the linear tetrahedrons in order so that there's not any error, but it takes a while to get there, and that the convergence once you get to that area is quite slow. Okay. Any questions on this? Okay, so this graph was pretty much kind of what we expected, except maybe the thing that was unexpected was just how big the error was for the linear tetrahedrons. Okay, let's move up in order. So let's look at the quadratic element. So let's look at quadratic tetrahedra and quadratic hexahedra. Okay, so once again, let's go ahead and draw our mesh convergence plot. Horizontal axis here will be the number of elements. Vertical axis here will be the tip deformation. Also, take note here that we are using deformation as our convergence criteria. If we were to try to use the stress, the convergence will probably look a bit different, but the same trends should occur. Okay. So once again, let's look at quadratic versus, or let's do tets versus hexes. And so for the quadratic tetrahedra, the graph would look something like this. Which you might be thinking, wait a minute, that looks exactly the same as the linear tetrahedron. So, do we get no benefit from switching to quadratic? Actually, you do. And the benefit here is in the numeric. And so if you look at where this graph starts, right? We're no longer starting at a very wrong number of 0.3 millimeters. Now we're starting at 0.74. So you can see that our starting point here, we're much, much closer to the true solution because we've switched to quadratic tetrahedron. So there's still a little convergence that's occurring. And so, you still get benefit from refining your mesh, but you're starting from a much closer location. Okay. Okay. And of course, the convergence here is at 0.75. Okay, now let's look at the quadratic hexahedron. So this is kind of the best element that you can have. So the convergence looks something like this. But once again, even for the quadratic hexahedron, we still have some converging to do. So you still get benefit from refining the mesh, but you're starting out from a much more accurate position. Okay, so these graphs also kind of pretty much what we expect. But you can kind of see here kind of the magnitude or just how much benefit you get from using a quadratic element. For structural FEA, it's pretty severe. And so definitely this graph here should hopefully make the case for using quadratic elements. All right, any questions on this graph here? Okay. All right, so before we get to the linear versus quadratic graph, so that's the last one. I do want to make a comment. And so if you notice that all of these graphs here, the convergence is always approached from below. So basically what that means is that when you have a coarse mesh, when you don't have enough mesh density in your mesh, you end up underestimating the deformations, and by that same consequence, you end up underestimating the stresses. And that's something that's pretty typical for most cases as well, right? And the reason for this is that if you have a coarse mesh, and so if your elements are too big, that actually adds artificial stiffness to your entire system. And artificial stiffness basically just means that the system is going to be it has a higher effective Young's modulus. I think that's probably the easiest way to think about it. It artificially kind of increases the Young's modulus so that the system is more stiff than it probably should be. Okay, and as you refine the mesh, that allows the system to kind of loosen up and kind of estimate higher deformations and higher stresses. Okay. So you should see that, when you do your mesh convergence testing for your project, everything that, your conversion should almost always be approached from below. Unless there's kind of a weird kind of a, sharp angle in your geometry that may cause the stress to kind of go up and down. Kind of like, the stress singularity that we talked about on Tuesday. Okay. Okay, so the last comparison that we're going to draw is between the linear and quadratic hexahedra. But this is kind of a foregone conclusion at this point. We should know kind of how this goes. Okay, so just like our other graphs, we're gonna have the number of elements on the horizontal axis, our tip deformation on the vertical axis, okay? Generally, what we should expect is that the quadratic hexahedra should converge faster based on the number of elements. And that's exactly kind of what happened. So let's start with the linear hexahedra. And of course, the thing that we need to quantify here is the starting point. And so the starting point for the linear hexahedra is about 0.72 millimeters. So a little bit worse than the quadratic tetrahedra, which makes sense because quadratic is really good for structural mechanics. Okay. And then if you draw the graph for the quadratic hexahedra, it converges much, much faster, kind of as expected. I kind of drew with the weird kind of up and down motion there. Just imagine that it's kind of a straight line. But the quadratic hexahedra, as we know, is going to converge much faster than the linear hexahedra. Okay. So these graphs here, they're just kind of a way to illustrate a point that we've kind of known for a long time. Use quadratic elements and use hexahedra if you can. But quadratic tetrahedrons are still a great choice for structural links. Okay. Any questions on these convergence graphs? Okay. All right. So next topic, kind of jumping around again, is we're going to talk about defeaturing. Okay. So defeaturing refers to kind of the act of taking a very fine or very kind of small detailed feature on the surface of your model and just kind of getting rid of it. So why would we want to do that? So a lot of times, when you have a CAD model, especially when you inherit a CAD model from someone else, and so someone else created the CAD model, maybe for design, maybe for some kind of mock-up, and they want you to do finite element analysis on it. Like we kind of talked about before, a lot of times those CAD models are not really designed for running an FEA. Because a lot of times, when you create a CAD model for another purpose, either for manufacturing or, maybe you're making technical drawings for someone to create to manufacture a part. Or maybe you're creating like a mock-up, something to kind of present to designers or something like that. These often produce a lot of extra things that are not needed in the finite element analysis. And sometimes, these extra things can actually harm your finite element analysis as well. Okay? So one feature or one thing that can actually mess up your FEA quite a bit are really tiny detailed surface features on your model. So what do I mean by this? And so, let me do a couple of examples to kind of show you. Okay, so the most common thing that I see that will cause errors in ANSYS FEA are threads on a bolt or threads on a nut, things like that. So if you were to create a CAD model for a bolt, it might look something like this. So you have the bolt head. And then on the shaft of the bolt, we have all these little tiny threads. And a lot of CAD softwares are really good at kind of, modeling all these little threads on the bolt, right? So those threads are important because you want to know that thread information when you are machining. You know what bolt to use, what to plug in, things like that. But something like this is a nightmare to try to mesh. Because what ANSYS is going to do is that if ANSYS sees all these little tiny, ridges on your surface, it's going to try to create a mesh that's small enough to conform to all those little tiny ridges on the thread. Remember, we talked about on Tuesday, what we kind of ended our discussion with was the difference between a patch conforming and a patch independent method. And so if you were to use a patch conforming method, then ANSYS is going to say, all right, these threads, they're part of the exterior surface. And so we're going to try to match this exactly. But in order to match that exactly, you have to create a really, really tiny mesh in order to accommodate all of those threads, right? And that's going to create a nightmare because what's going to happen then is that in this really tiny bolt, you're going to have all these really, really tiny little elements. And then that's going to create a huge imbalance in terms of where your mesh density is assigned. So you're going to have, sometimes hundreds of thousand elements dedicated to these tiny bolts. And, the actual part of your structure, which is actually supporting the load, is going to have much less elements. So that's probably the most common thing that I see, especially for structural FEA, because these bolts are often, they're often included in these CAD models. And so, if you are going to do a finite element simulation with bolts there, maybe you want to find out kind of what the stress on these bolts are. So you can leave them in the model, but you have to have a way to kind of suppress these threads in a way. Otherwise, your mesh is just going to be completely crazy. So that's something that's important to do with threads, okay? Another common case for this is, maybe small fine cosmetic features that might be on the exterior of your mesh, of your model. So one example of this is, let's take our original activity with the plate with the hole. And let's say that we took this part and we made a little tiny ridge around the hole. So we made kind of a little bit of an indent of maybe like a 1/16 of an inch or an 1/8 of an inch down into that hole. Say that, we made 1/8 of an inch. This would be something that, normally might be imprinted really quickly, or, if it's a more complex pattern, maybe it's etched onto the surface, okay? These would often be included in the CAD model just to kind of show what the part would look like in the end. But again, this is going to create a hell for your mesh, right? Because if you look at kind of a side profile of this ridge, oops. So if you look at kind of a side profile of this ridge, right? You're going to have a situation where you have kind of a little step here, where the height of this step is only 1/8 of an inch. Right, because we basically just kind of imprinted that small ridge in there. Okay. And so ANSYS is going to see this, and so ANSYS is going to say, all right, we have this small feature here that's 1/8 of an inch, deep. And so in order to capture it, then our mesh must also be at most 1/8 of an inch. Okay. So ANSYS is going to see this. It's going to say, all right, I need to make my mesh smaller to kind of capture this detail well. Again, because of the patch conforming method that ANSYS likes to do. So it's little things like this that can really kind of kill your mesh, and you'll be kind of pulling your hair out trying to get a good mesh density on it. And it's just not going to happen while those features are there. I see this every year, when I teach the undergrad version of this class. And so, for the final project, also the final project for this class too, I let you guys kind of choose your own geometries. And a lot of times the undergrads kind of pick kind of the project that they're working on for senior design to run an FEA on. And oftentimes the CAD models that they're working with for those projects have these really, really tiny fine features, or maybe they have bolts with threads on them, and and they're getting meshes with 500,000 elements, and they're like, I don't know what I'm doing wrong. And it's because they have kind of small features like this, right? So this is definitely something to look out for. And so what can you do if you have a situation like this? So let's say that you inherited a CAD model, and let's say it has these features, what are your options? Well, the best option would be, if you're able to modify the CAD file yourself, the best thing to do would be just to kind of remove all these kind of fine features, suppress the threads or suppress these kind of small indents, and kind of recreate the CAD model. Sometimes you have the ability to do that. So if you're able to do that, that would be kind of the best thing, but there are some tools within ANSYS itself. That you can tell ANSYS to kind of try to ignore these features to the best of your ability, or at least try to prioritize a high quality mesh over trying to capture all of these little details individually. So one option, we've already kind of talked about last time on Tuesday, which is to use the patch independent meshing method. Remember, we talked about last time that patch independent is going to create your mesh from the inside out. Maybe not necessarily following or conforming to all the surface features, but with patch independent, it's going to prioritize creating a high quality mesh over trying to capture all the individual details. So that's another method that actually works pretty well in a lot of cases. Okay. But there are kind of more other options within ANSYS itself that you can use as well. Because sometimes, sometimes you'll have features on the surface of your model which aren't really there. They may just end up being artifacts from how the CAD model was developed. And so this tool called virtual topology is useful for kind of getting rid of those superfluous kind of features. So the way virtual topology works is that if your CAD model has a lot of extra contours, a lot of extra kind of edges that are not really there, but were kind of just created just as a result of the CAD model, virtual topology will let you kind of combine those together in kind of a very kind of smart, intelligent way. Okay, so this is very common when you have when you use a CAD software to create a curved surface. Maybe not a circular surface, but maybe kind of an irregular curved surface, like an airfoil or something like that. Okay. So let's say that you have kind of a moon-shaped structure that kind of looks like this. It kind of has like an irregular curvature to it. And so because of this curvature, there's kind of a lot of extra contours that get produced in order to capture that curvature exactly. Okay. So these extra contours here, they're not actually part of the model itself. They're just kind of artifacts from the CAD process. But this is actually going to create kind of a headache when you're meshing, because ANSYS is going to see these extra contours or extra lines as kind of breaks in the model. So when it goes to create the mesh, it's going to create, there's going to be kind of a natural line that kind of goes across like this. And so your elements are going to be kind of very clearly separated by this line right here. Okay, but you can eliminate these extra lines through the virtual topology tool. And so if you use virtual topology, then it kind of recognizes that, okay, all of these contours are kind of part of the same surface. And so let's kind of eliminate them and kind of create one smooth surface for us to mesh altogether. So after using virtual topology, you kind of have a nice smooth surface just like this. And without those extra contours, without those extra surface features, this is going to create a much better quality mesh. And so to access virtual topology, you can actually access it directly from ANSYS Mechanical. And so it's accessed from the geometry tab. So that's kind of where you assign material properties and things to your parts. And so if you have a surface, if you have a CAD model with a lot of curvature, this might be something you look into to help kind of improve the quality. So for those of you that are doing the four-way valve, or even the office, actually the office chair is actually a great example of this. So the office chair has a lot of extra contours on it. So for those of you that are working on that model, because the office chair is a great example of, a lot of weird curvature to make it, that's done to make the chair ergonomic. But it kind of makes it a little bit more difficult to mesh. And so, this might be a feature you look into if you're doing that geometry for your midterm project. Okay, another feature within ANSYS to kind of help with this is called automatic mesh-based defeaturing. So this is a little bit of a less manual process, and so it's convenient, and so with these kinds of things, you'll see that in ANSYS and in any kind of computational software, there are some settings and some things that you can do which are kind of more or less automatic, which is convenient when it works, but it sucks when it doesn't work because you don't really have any control over how it actually is going to do things. But the idea behind automatic mesh-based defeaturing is that this lets ANSYS kind of actively ignore features on the surface that are too small to mesh. Okay, so the way it works is that you're going to specify a length scale or a size of an element of a feature that you want ANSYS to ignore. So this would be a good feature if you have a lot of threads, if you have a lot of bolts in your CAD model, and all those bolts are of a certain feature of a certain width or a certain size, and so you can just tell ANSYS to ignore everything that's less than 1/8 of an inch. Then it'll kind of automatically do that and produce for you a much nicer mesh. Okay. Okay. There is kind of a small way that you can kind of control this. And so let's say that there are features that you actually want to preserve in your final mesh. And so you can kind of save those as what's called named selections. And ANSYS will kind of ignore those. So it'll ignore the ignorance, I guess. And so it'll include those in the mesh. But this is a nice way to kind of give a blanket kind of setting. So say ignore everything that's smaller than this. And that'll kind of produce you a good mesh from it. Okay, and so this setting here, if you want to activate this is again, this is also accessed within ANSYS Mechanical. This is accessed within the global meshing settings of ANSYS Mechanical. Right, so defeaturing is one thing that, you'll probably spend a lot of time with if you're working with kind of, industry kind of CAD models, just because those CAD models are gonna have a lot of these features. Generally, my rule of thumb is, if you're not sure if you should defeature something or not, you should ask yourself, is this feature or is this part of the model, is it going to contribute to the structural strength of the model? Is it going to contribute to the, its thermal properties, things like that? If the answer is no, then probably you should defeature it or suppress it in some way. And sometimes the answer is yes, and so sometimes it's surprising. So think about, not only think about your geometry, but think about how your geometry is going to be loaded as well, right? Because a lot of times, these tiny kind of imprints or these shallow imprints that are on the surface, that's actually where your part may interface with another part, and there might be forces that get applied there. And so in those situations, you would actually want to keep those features because they're actually important for the structure itself. And you're going to have stress magnitudes, stress concentrations in those areas. And so in those cases, you would actually want to keep it. But if the feature is just mostly cosmetic, or if it's abnormally small, then in those cases you want to suppress it. Right? So it's definitely a case by case basis, and it's something that you kind of build intuition for as you kind of do more FEA. But it can really give a really big headache with meshing if you're not careful. All right, any questions on this? Okay, all right, so that's all the time that we have for today, so we'll wrap it up a little bit early. So when we come back next week is going to be all in preparation for activity 5. So on Tuesday, I have kind of a short lecture about that, and then next Thursday we'll do activity 5, and then we'll go on from there. So thank you guys for coming today. I hope you guys have a good rest of your evening, and I will see you guys next week. That's actually not for deformation. So remember the shell elements, they also solve for the orientation. So I think that's just illustrating that. But it's not actually. So it looks good, but let's look at it again. One way that you can fix it is that you can change that displacement support to just a fixed support. I think that's one of the data points too. And I think people are getting much better results. But it looked good to me, but if you wanted me to look at it again. And you did a bunch of work after that. Oh yeah. So sit down. Yeah, the results can be a little bit weird to look at what happens cell. But it looked fine to me. The main thing I'm looking for is that like when you apply the downward force on the like you have those kind of patches of where there's deformation. For that, does that look correct?
I guess like when I was So much.
Yeah, that's.
I didn't do as.
Okay, let's.
Yeah. Oh.
Oh, you're in space.
Very size not. But it's kind of thing. Yeah, I mean, that's just the answer. Yeah. How's your son feeling? Is he feeling better? That's good.
Broke.
Yeah.
Well, I mean.
Oh.
No.
Like
my smile.
Yeah, yeah.
It was just terrible interesting because she's only 2.
Oh.
Right.
Oh no.
Because we were talking about like her brother.
Yeah.
We have to take him for a while.
Yeah.
Okay.
Yeah, yeah. Yeah,
So
that's
where's the old one?
Sounds good. Okay, so yeah, let's look. So how much pressure? Pressure on this one. 20 PSI. Deformation. So this model is actually not that big. So even though I say it's a bridge, it's actually not a full scale bridge. So you can see it's
Yeah, it's less than.
yeah, it's like a toy bridge.
Yeah.
So but I think what I would test to see. So the deformation right now is about 0.3. If we double this, the pressure or the deformation should go up. Which is 60 PSI.
That warning message.
Let's see. One more. Okay, yeah, so that's just a warning to say that, it thinks that the model is under constraint. And that's mostly just because of this displacement. So I gotta change this activity because I think, yeah, it's kind of gives some unintuitive results. But yeah, but the deformation kind of did exactly kind of what we thought, where if we double the load, then the deformation doubled as well. So I think it's working fine.
Oh, okay.
Yeah, yeah, so that warning, I think if you change this displacement support to a fixed support, it should make that go away.
Okay.
But yeah, this looks fine. So so we see kind of these contours where the displacement,
Yeah.
the beams are doing what they're supposed to be, they're supporting the bridge, so we're seeing less deformation at the beams.
Yeah.
And they're more kind of, so yeah, this looks good. I think if you see that, if you change, so I think the other thing that people are concerned about is the stress. Because the stress is all kind of concentrated here.
Yeah.
And so that's kind of another thing too, where if you change this to a fixed support, then the stress is going to be more even.
Even. Oh.
Yeah, yeah, but everything else looks good. Yeah, yeah, I'll be there in a second. Yeah, and then just make another fix support. But yeah, it was good.
Thank you so much.
Yeah.
Thank you.
Oh, yeah, yeah, so the arrow that they put there is just for rendering. And that's how they're applying it. And so it's applying it the arrow is just there just to show you whether it's on top or below.
That's the one.
Okay. See. Do we have another force beside it? Oh, okay. Because I was saying that we just have the downward force.
I feel like, well, I see the person, but I feel like. That'll go.
Okay, so in this case, it looks like the wind force is that. Well, we found. This looks right. This is that the wind force is just going to do so much. If you're applying the wind force here, there's a much bigger moment. It's getting hot like that. This looks fine. So the thing that I think is concerning for a lot of people, actually this boundary condition here. So I think you're gonna get results that. I was just telling you this to change this to a fixed. I should really change this to this. I have this here just to kind of show people what this place and support that, but. Yeah, I can change that to a fixed support that's gonna make the stress positive. Right now, all the stress is kind of concentrated. But if you change that to a fixed support, it's kind of been distributed along. Yeah, besides that, I think it's like this.
To this was originally spent.
What did you think? Oh, the service. I think the easiest way to probably should read down. It was this in this session that we. Control Z that
It wasn't in section 9. In appearance, get rid of all the parts where it's technical.
oh, okay, I see. Yeah, unfortunately.
So when I did that, it cut out a new this is.
Oh.
So
That would be an issue.
this one here.
I think there might be. I had a. Stress. Yeah, that's gonna happen with the stress. With stress, it's gonna be harder to convert, especially with. Especially max stress. Max stress is even harder. There might be an area where this is concentrated, but you might want to do that. And so you can find that area, okay, that's likely going to be hard. If you found a single area where something fully. So one thing you can do is that you can cover stress. Yes, I'm making sure you know that. We figured that out. Even that application. Probably I might be international.
Stress was concentrated.
Yeah, that makes sense. Right, that's probably where that's what most of the. Yeah, max stress is gonna be important. You can put a valve. You get over. I'm just not interested to see how it goes. This is a very complex cat. I'm not surprised that it is cool.
The eight scenarios with
That is true. That is true. That's fair.
Yeah, I think I live really much. Yeah, I went to the dentist last week. Hey, that's what we're doing. Yeah,
You can try to, well, really this.
so much.
Was that in this section? You can both see. Oh, no, good.
So sorry. That was problem.
I thought we were, I will still be through. You know, why you counted that? I would just be more positive. For them, it's like.
Like the, you know, the fifth way. Like, God, no, like.
Yeah. If he had created it based on like something he did, I would have probably got it.
Also, we need it based on the back.
Yeah.
So like,
Yeah.
I mean,
I made the same mistake.
So yeah, it's not the whole.
You know what, I'll give you that. I thought the only thing I did wrong was.
So this one looks correct, this one is the tips. Yeah. Yes. It's kind of annoying. Yes. I did the same thing. Funny, sir, getting last evidence. We wanted to actively. Yeah, let me finish.
He says C should be half of this.